Hello, this is the next video in a playlist that I'm calling Complex Variables, where we're going to do a playlist on complex analysis. But first we're covering complex numbers, and today's topic is the complex polynomial with degree n, or of degree n. So the polynomial equation is if a0, a1 through an, and z are all complex numbers. Of course, a0 cannot be 0. Then a polynomial of degree n, where n is integers, positive integers, is written like this. So the goal that we're going to look at is to find the solutions to f of z equal to 0. These are the z that makes this happen are called zeros, or roots of this equation, or of the polynomial, and we'll derive some special properties in these regards too. Now, the first theorem is the fundamental theorem of algebra that states every non-constant single variable polynomial with complex coefficients has at least one complex root. Now, that's the original theorem. My remark is an equivalent theorem that I think most people think of as the fundamental theorem of algebra. And the theorem is also stated as follows: every non-zero single variable degree n polynomial with complex coefficients has, counted with multiplicity, exactly n complex roots. Okay, so along those regards, let's look at the rational roots theorem. So let a0 through an, p and q all be integers, right? So the fundamental theorem says that these can be complex numbers, but in the rational roots, they all have to be integers. P and Q are co-prime, which means the largest common divisor is 1. Z, of course, is a complex number. And our polynomial, nth degree polynomial, is f, is written like this. Now, if the fraction P over Q is a 0 to the equation, i.e. plug it in and you get 0, then P is a factor of an and Q is a factor of a0. So let's prove that. So first let's show that P divides an. Now, since P over Q is a 0 to the equation, this first one is true. And what we're doing is plugging P over Q, P divided by Q, into the polynomial. And since it's a 0, it makes it equal 0. Well, let's multiply both sides of this equation, Q raised to the nth power. And so it goes away here. There's, one of them here, and it goes on down here. There's n minus one of them left. Here there's qn, right? It still equals 0. Let's take this term here on the end and subtract it to the other side. So that's the minus an q raised to the nth. But then let's divide every term by p, right? So there's one less here, there's one less here, all the way through. Now, on the right side, notice that everything is an integer. All the a's, a0, a1 through an minus 1 is an integer. P is an integer, Q is an integer. And so all these binary operations creates another integer. So that says the number on the left-hand side of the equation is also an integer. But P and Q are co-prime, which then, to make this an integer, P must divide into an to make this an integer. And that's the quick proof that P divides an. Now let's show that Q divides a0. Now, since P over Q is a 0 to the equation, let's plug it in. Let's multiply, both sides times Q over n, and we get some cancelizations. We get this. But let's take this first term and divide it to the other side, or subtract it to the other side. And so we get this. So nothing's changed, but we've subtracted that over. Now let's divide every term by Q, and we get some cancelizations and over here. Now look at the right-hand side. The right-hand side is binary operations of integers, right? So the right-hand side is an integer. That says the left-hand side is an integer. But Q and P are co-prime, so they don't divide into each other. So that means Q must divide into an. And that's what we wanted to show. And so we've proved the theorem. And at the end of the video, we'll do an example to illustrate this. Now we can factor a polynomial if we know, so this is called the factored form of a polynomial. If we know the zeros or the roots, z1, z2 through zn, let's assume they're the n roots of the nth degree polynomial f, then f of z, the polynomial, can be written in this form, its factored form. And the way I see this, if we set f of 0 to equal to 0, that means we set this to 0. And we have the product of numbers equaling 0. That says that at least one of these products must be 0, so we can solve for solutions, and it's easy to see that z1 or z2 and zn are the zeros. Anyway, this is called the factored form of a polynomial. Now let's the next theorem, let's let a0, a1, an, and z all be complex numbers, and let f be a polynomial of degree n, so it can be represented like this. Now the first term, of course, can't be 0, right, in order for it to be degree n. The sum of the zeros of the polynomial, so the zeros are z1 through zn, and the sum of these are equal to minus a1 divided by a, and that's the coefficients on this polynomial. Also, the product of the zeros of the polynomial are equal to minus 1 raised to the nth times an divided by a0. Now let's prove that. So since z1 through zn are the zeros of this nth degree polynomial, we can write it in this fashion. So, and 0 is equal to this. If we plug in any one of these into the polynomial, we get 0. But let's multiply this right-hand side out. If we were to multiply it out, we're going to skip several steps. The an comes down, but then of course if we take zn multiplied times all the z's, we get z to the nth power. And now look at an to the zn, that's the original, right? But if we collect all the terms that are the n minus 1th power of z to the nth minus 1, these are the coefficients. It's minus that. And I'll let you do the math there, but go through it at least once, maybe look at like a 3rd degree polynomial, then a 4th degree polynomial, and prove it to yourself. And then if we multiply all the last terms, we get the product of these z's, or these zeros, but we don't know if it's positive or negative because it depends upon if n is even or odd. So that's why we have minus 1 to the nth power. But if we equate the coefficients, look, the coefficient of the n minus 1th power is a1. That has to equal to the coefficient in front of z to the n minus 1. Now don't forget the a coming in. So let's equate these coefficients. So minus a0, and the sum has to equal a1. This coefficient, now don't forget the a0 multiplied in, has to equal, and then the product is a to the n. Now this should be a plus, dang it. And so I'll fix that in a hard copy. But then we're finished. Solving for the sum, you divide that over, and that's what we said it was equal to. If we divide these two terms, remember that's a plus, over to this side, well, that's what we said the product of the zeros equals, and that's what we wanted to show. Now, the zeros of the next theorem, the zeros of a polynomial with real coefficients occur in conjugate pairs, and that to me is kind of cool why it happens. So let's let z1 be a complex number that's a 0, so it's a complex 0 of this nth degree polynomial, right? And we want to show, now notice that the coefficients are real, so all the a's are real numbers. And we want to show that the complex conjugate of z1 is also a root to this equation. Now there's one piece in this theorem, and I'll point it out, that we haven't proved in this playlist, and if there's a need for me to prove it, just put it in the comments. I'll gladly prove it. It's a straightforward proof, but I'll show you when we get there. So remember, z is a 0 to this polynomial. So we plug in that value for z, right? And that equals 0. Now, if we take complex conjugates of both sides, now this is a real, so the complex conjugate is just itself, but we take the complex conjugate of this. Now, earlier in the playlist, we showed that the complex conjugate of the sum of numbers is the sum of the conjugates. So then we take the complex conjugate of each term. But the a's, a0, a1, an, are all real numbers. So it's the complex conjugate is just itself. So we're taking the complex conjugate of this term. Now, this is the step that we haven't proved yet in the theorem. The complex conjugate of a complex number raised to a power is just a complex conjugate raised to that power, right? You can almost, it's like you take it into it. And it's a straightforward induction proof, like 3 or 4 lines. Okay, so that's the step we haven't proved yet. But then the complex conjugate of a complex number in polar form is just the negative of that number. So we put in the complex conjugate. But here we're saying that we're plugging in the complex conjugate into this polynomial and it equals 0, right? So that says the complex conjugate of z1 is a 0. So that says both z1 and the complex conjugate of z1 are both zeros. And that's what we wanted to show. Now, quick example, let's find the zeros of this 5th degree polynomial. Now notice all the coefficients are reals, so we're going to use the rational roots theorem to possibly find a root. Now you take all the factors of 4 and all the factors of 1. So the factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4, and then you divide each of those, all the possibilities for the roots of 1, which is just 1. So that says the possible rational roots of this 5th degree polynomial are these. Well, if you plug in 0, you get 0. I mean, you plug in 1, you get 0. So 1 is clearly a 0, and then we use long division to get this equation. Now we use the rational root theorem on this. Now it's the same possible rational roots, plus or minus 1, 2, and 4, but you can plug in 1 for z and you get 0, so it's clearly a 0 of this 4th degree polynomial. Then using long division, you can get this expression. Then the rational roots of this are the same, plus or minus 1, 2, or 4, and you can show that if you plug in 2, you get a 0 to this 3rd degree polynomial, and we use long division, we get this. Now this is a quadratic equation, and we have the previous video in this playlist is the quadratic formula, and so we can use it and we get minus 1 plus or minus I, or the roots of this quadratic. So that says the zeros to this equation are 1, 1, 2, minus 1 plus I, and minus 1 minus I. Okay, I'm running long, so I'm going to quit. The next video will be the dot and cross product of complex numbers. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.